At the bottom of page 621, I want you to write, prove tan squared theta plus 1 equals secant squared theta. So it's a proof, so we draw our line. Now, the reason you're never going to be asked this again is if you look on your formula sheet, formula number 3, right underneath sine squared theta plus cos squared theta equals 1, is tan squared theta plus 1 equals secant squared theta. So if this was a proof on your final exam, all you would have to do is say, well, tan squared theta plus 1 is secant squared theta, and you would be done, and you proved it. Because you're going to be allowed to use anything that's on your formula sheet, plus all of the reciprocal ones, like tan is sine over cos, cotangent is cos over sine, secant is 1 over cos. Those are the ones you're allowed to use. But let's say I hadn't given you a formula sheet yet, and we only knew our very first strategy. So our very first strategy is, can you change things to sine and cos and get a single fraction on both sides? Okay? Now, if tan of theta is sine of theta over cos of theta, then tan squared of theta is sine squared of theta over cos squared of theta. And if secant theta is 1 over cos, then secant squared theta is 1 over cos squared theta. And we want to get a single fraction on both sides. This side has 2 fractions being added. How do I add fractions? I need a common denominator. So I'm going to get a common denominator of cos squared theta. So I multiply this top and bottom by cos squared theta. And then I get a single fraction. Whoa. Let's go. My common denominator is cos squared theta, and I can add the tops, which will be sine squared theta plus cos squared theta. Now, generally what happened was after you got a single fraction on both sides, in our previous proofs we've been done, but these ones aren't the same yet. However, do you see the big idea? Then on the top here I have sine squared theta plus cos squared theta. What's that always equal to? 1. And since that is on your formula sheet, you are just allowed to change it to a 1. And now my left side equals my right side. QED. What is that? QED, again, is shorthand for Latin for like I'm done. Quod erat demonstratum. Or something like that. I should really work on my Latin.
Does it actually mean I'm done?
Well, what has been, what was asked for is demonstrated. I'm done. Yeah.
Can you just write I'm done?
No. No, not allowed. You have to use either the abbreviations in Latin or...
If I leave it out, do I lose marks?
No.
Good, then I'm not going to win. Yep, all you use is 3 dots.
It's just so much fun.
Do I need
You don't
the 3
need
dots?
3 dots though, do
You do need, therefore, left side equals right side.
You need the 3 dots?
Yes.
What error would that be if you did?
What do 3 dots mean? Therefore, which we had a great discussion about before. That why is the short form for therefore 3 dots? There should be 4 dots, but it's only 3 for therefore. Okay?
If they leave out the ls equals rs, is that the error?
It's just you didn't finish yet.
So you didn't finish the textbook.
Okay. So here we've done a proof, and now you have, we could do the same thing with 1 plus cotangent squared equals cosecant squared. These are your Pythagorean identities. And you are allowed to use them at any time in a proof. Today our proofs get more difficult because we get more strategies. And our main strategy, although it's great and usually works, sometimes doesn't work well. So we're going to have some other situations where we do new strategies that will work better, and how to recognize when there's a better strategy available. So for example, we already have seen, like, in some of our solving questions, we sometimes replaced either sine squared theta with 1 minus cos squared theta, or cos squared theta with 1 minus sine squared theta. In a proof, if you have a 1 minus cos squared theta, even though it doesn't match up perfectly with this identity, you can change it to a sine squared theta without showing any work. Anything that you can get from these three formulas with only one mental math manipulation is fair game. So for example, if you see a question that just has tan squared theta by itself, can you see one mental math manipulation? I can move the 1 over to the other side and be like, perfect. So you could change it to secant squared theta minus 1. No marks taken off. I'm going to write something that's true where you would lose marks. Let's say in a question you had negative cotangent squared theta, and you just wanted to make it 1 minus cosecant squared theta. Can you see that that is true? Can you take this one and manipulate the equation to get that? It's not very hard, is it? Well, if I move this to this side, I'd have to subtract.
Yeah.
And if I move this to this side, I'd have to subtract. So I would get negative cotangent squared by itself. And on this side, I'd have 1 minus cosecant squared. Okay? But you will lose marks for that because that's 2 mental math manipulations you did. You have to draw the line somewhere so that people don't just go, oh, yeah, I just did this all in my head and I got this. You have to show work. So this wouldn't be allowed, but these would, or just anything that's one change, you can use at any time. Okay? So, we're going to go to example 1, and we're going to see some places where maybe we want to use some more strategies. I'm going to cheat here. Step 1 is rewrite the question. I'm cheating because I'm not rewriting it. And then draw the line. There we go. And for example 1, we're going to use the main strategy. Because sometimes there's shortcuts. Like on this side, I'm like, ooh, cotangent and tangent. I can change cotangent to 1 over tangent. Maybe this is a good idea. It would be if you can change the other side also to tangent, but you can't. So it was a good idea, but it's not. Okay? So I'm going to use the main strategy. I'm going to change cotangent to cos theta over sine theta, and tangent to sine theta over cos theta, and cosecant to 1 over sine theta, and secant to 1 over cos theta. On the right-hand side, if you're multiplying fractions, multiply the tops, multiply the bottoms. Single fraction. On the left-hand side, I'm adding fractions. How do you add fractions? We say a common denominator. So the same thing on the bottom. In other words, I would have to multiply this bottom by cos theta and cos theta, and this one by sine theta and sine theta. And you know how there's not very much room? You might be tempted not to write the theta. If you forget a theta once in a proof, you get an E3 error.
Can we do like 2 cos theta and 2 sin theta on the top?
Don't. Because what happens if I do cos theta times cos theta? I get cos. First of all, the bottom is now a common denominator of sine theta. I don't want green, I want it black. The bottom is now a common denominator of sine theta, cos theta. But if I do cos theta times cos theta, I don't have two cos thetas. That's if I add. If I multiply, I'm going to have cos squared theta.
Okay.
And sine theta times sine theta, that will be sine squared theta. So main strategy is done, but we're not done. We got a single fraction on both sides, but they're not the same. Can I do anything with cos squared theta plus sine squared theta?
Yeah.
That's my big idea. That's a 1, so I can change it to 1. And now I am done. I don't know if I like actually do this much. Yes.
Is there like a page with like a list or any like showcase of CSC equals 1 over sin theta?
Yes. It's in our notes, in our book. And it was in section 7.3 on page 686. They are sort of a must-have memorized. In fact, even these new proofs, like the tan squared theta plus 1 is secant squared theta, it's on your formula sheet, but you have to have it memorized for AP Calculus next year. And if you don't have it memorized while you're doing proofs, you're going to miss out on shortcuts on proving. So you kind of have to memorize it already this year as well. Right, part B. This is the first one that if you decide to change to sine theta and cos theta, it's a little bit annoying. So we're going to use a shortcut in this one and a new strategy. The new strategy is if you can see a way to change everything to just one trig function, usually that's better than even changing to sine and cosine. Like one of the reasons the number one strategy is change to sine and cosine is it simplifies things down to two trig functions. But if you can have only one trig function, it's even better. So I look at this question, and one of the strategies I'm going to write down for you later is like, make sure you look at both sides before you start. Maybe a shortcut jumps out to you. I look at this one, I see a lot of cotangent theta. The only thing that's not a cotangent theta is the cosecant squared theta. But that's one of my new formulas. My new formula says there's a relationship between cosecant squared theta and cotangent squared theta. So I'll draw my line, and instead of writing cosecant squared theta, I look on my formula sheet and it's equal to cotangent squared theta plus 1. And now my proof has only cotangent. So chances are, if I simplify, things should work out. Now I distribute this cotangent. Cotangent times cotangent squared is cotangent cubed. Cotangent times a plus 1 will be plus cotangent. And then I have a minus cotangent at the end. And a plus cotangent minus cotangent, that'll be 0. So I'm just left with cotangent cubed theta. Not too bad. I'm gonna add actually one more in here. So there's another strategy that I want you to see. Oh, it's in blue, so I'll stay in blue. Prove, oh my goodness, a 4, a tan to the 4 minus a secant to the 4 equals negative tan squared minus secant squared. Once again, you could change everything to sine and cosine. Highly not recommended in this situation. A very important strategy that comes up a fair bit is factoring, particularly factoring difference of squares. Do you remember what a difference of squares is? Like if you have a simple example would be x squared, which is a square, 9, which is 3 times 3, with a difference in between. These factor really nicely to x plus 3, x minus 3. This is a difference of squares. Now we're going to have differences of squares appear with trig functions. We don't have it on the right-hand side because there's an extra negative. But we do have it on the left side, so we can factor. Tan to the 4 is a square because it's tan squared and tan squared make tan to the 4. Secant to the 4 is a square because it's secant squared and secant squared. One with plus, one with minus. That's factoring a difference of squares. Now I'm going to lose a mark, so don't write down the next step quite yet. I'm going to lose a mark because I'm going to do this. It's not wrong, but I still have to lose a mark. Can you see what I did to change this one to this?
More than one mental math.
More than one mental math though. I can easily get tan squared theta minus secant squared theta on one side of that equation, right? But then I'd also have to move the 1 over to the other side. So I did 2 mental math things to do that. So I would lose a mark for 2 mental math manipulations. You want to see 3 mental math manipulations? If this was 2, the third one I'll distribute the negative, and then I'd be done. So you can see why this is problematic, because when people get stuck, they just sort of write down the other side and hope that they were close. Bad idea. Lose marks. Sometimes you lose more marks for that than you would have if you just stopped. Okay, so what do I have to show? Well, I'm going to need more space. There we go. I know that secant squared is tan squared theta plus 1, so I could replace the secant squared with tan squared theta plus 1, like that. That would be all, that would be allowed. And then tan minus tan is 0, negative distribute, that's negative 1, that's fine. Now you could write the negative. And now I could distribute that negative 1. Almost distribute it. So, questions 5, 6, 3, but 6, I only, 7, I, and 9, I. Because I think the I is just, that's the part that's proving. I might be verifying or doing extra stuff that I'm like, you don't need to do that. If you didn't factor the difference of squares, the proof becomes very difficult. So it's a very good strategy if you can factor that you'll want to factor.